Welcome to today's Trane Engineers Newsletter Live program. I'm Jeannie Harshaw, and today we'll discuss modern unitary heat pump applications. We'll start the program by covering the history of heat pumps and some misconceptions that surround them. Then we'll discuss how heat pumps can be applied in common systems as well as efficiency requirements. Next, we'll discuss common nomenclature and heat pump terminology. And we'll finish with sequences of operation, heat pump selection, and energy modeling. To cover today's topic, we have application engineers Greg Duchesne and Eric Sturm, who are joined by Raymond Russick, a technical product support engineer, and Abigail Williamson, a unitary commercialization leader for Trane Commercial. To get us started, I'll hand it over to Abby to discuss the history of heat pumps.
There are lots of questions surrounding heat pumps. For all of us in the industry, it seems to be the current buzzwords. For starters, what are they? How do they work? And then for us industry vets, those questions go a bit deeper into, well, why are we talking about them so much? Maybe you live in an area that doesn't see this trend yet. For example, gas is cheap here. Our electrical grid isn't the cleanest. We don't see legislation changing anytime soon. Or maybe you live in an area that's cold and fossil fuel heating is perceived as being necessary. And in some cases, air source unitary heat pump technology is limited to certain capacity ranges. So maybe you don't see the benefit yet, but there are. And as this trend progresses, it will continue to not only grow around North America, but also in technology. In the next few slides, I'll go over the history, the benefit of using heat pump technology, and then move on to cover some common misconceptions as far as their operation capabilities. And then we have a fun-filled cast, including myself later, to break it down into further detail. The concept of heat pumps have been around a long time, dating back to the early 1800s. From Oliver Evans' description of the vapor compression cycle in the 19th century to Carnot's initial work on heat engines and his concept that led to what is now known as thermodynamic reversibility. These and many more led William Thomson, or better known as Lord Kelvin, to the first known documented heat pump idea about 170 years ago. Kelvin, the one you know for the Kelvin temperature scale, was clearly vested in the now fundamental laws of thermodynamics. Throughout the 20th century, significant advancements in heat pump technology emerged. Innovations such as more efficient compressor designs, the use of environmentally friendly refrigerants, and improved system controls helped shape the modern heat pumps we have today. While the early heat pump applications relied on heat sources like lakes and groundwater, the 20th century saw the widespread use of air as a readily available source. Today, air source heat pumps are extensively utilized for their versatility and energy efficiency. In this presentation, we will focus on air source heat pumps, exploring various advancements and additions to the field. So why heat pumps now if they've been around so long? The number one reason is climate change. Some of our younger viewers may recall learning to love and care for our Mother Earth from a couple of early 1990s cartoon climate advocates, and in turn, the industry has started to align with this and ways to mitigate this. There are several pillars of decarbonization: energy efficiency, electrification, renewable energy, and refrigerant management. Heat pumps play a role in many of these, certainly electrification being the big one. And regulatory changes will continue to push this. One big fact to back this up is that roughly 42% of global CO2 emissions are generated by our built environment, of which HVAC plays a pivotal role. So looking into the future, we can play a large part. Another why is monetary savings. And cash money tends to rule the world, as well as make it easier to make decisions, kind of like me on any kind of sale. Whether through straight kW savings at the meter incentives, fees like carbon caps or carbon pricing, heat pumps can show the customer a real savings. As we'll talk about later, heat pumps only gain in heating efficiency as the ambient temperature increases, and many grids are ready for this through electrical rates. Another benefit are the national and local incentives available through utility rebates and IRA incentives. It goes without saying that these benefits will further expand as our perspective and regulatory landscape evolves. Returning to the fundamentals of Heat Pump 101, and its most basic essence, heat pump solutions do not create heat. Instead, they transfer heat from places where there's a surplus to places that require more. So envision a regular HVAC unit operating in cooling mode and simply flip it and reverse it. Heat pumps achieve this through the utilization of a four-way valve and use electricity to deliver both heating and cooling to a building. During the winter months, a heat pump generates heat by extracting heat from the outside air and transfers it inside. Alternatively, in the summer, it can provide cooling by moving heat from the inside of the building to the outside. This design can be applied to both packaged and split systems. Some people, particularly those in colder climates, may be hesitant to go all in on all electric heating. Hence, hybrid dual fuel units were created. Similar to hybrid cars, hybrid dual fuel units provide the reassurance of a combustion engine plan B. In many cases, the biggest benefit to people is peace of mind. Building operators are often surprised by how infrequently gas heating is used. For many split units, which do not have dual fuel as an option, auxiliary electric heat is used like non-hybrid heat pump units. Often, these units can come in both standard and high efficiency. Later in the program, we will discuss the standard sizes from the industry, which in the commercial realm is typically up to 25 tons. But this limit will change over time. Now, we will move on to address some misconceptions regarding heat pump technology. Technological advancements allow heat pumps to work well below freezing outdoor temperatures. And dual fuel units, as discussed prior, can provide a hybrid approach, using the electric heat pump as a primary heating method with an auxiliary natural gas heater activated only on the coldest days. As shown in the light red, the changeover temperature range from heat pump to natural gas can be adjusted to occur between 15 and 45 degrees Fahrenheit, dependent upon the customer's goals for balancing comfort, payback, and emissions reduction. Hybrid dual fuel units are especially attractive for replacements where buildings have existing gas lines and carbon reduction is a priority. Many gains are being made on the smaller tonnage footprint for lower ambient versions, and this will only start to creep its way into the commercial-sized tonnages. So now on to the question, is the grid ready? Will this even benefit my customers financially? And that's a tougher one. But looking at the current data, there are certainly sites with much cleaner grids. Later we'll go into specific examples, but for now, for the most part, yes. Moving to a heat pump or a dual fuel unit will benefit many customers in North American regions. So for the time being, we can't have a carbon-free building if you are burning fossil fuels in them. But after moving away from such means, should the source move to a cleaner power, such as solar, wind, or nuclear, we get closer. And to kick the rest of this presentation off, let's move over to Eric to discuss their use in common systems.
Let's next discuss how heat pumps might be applied in a system. Ideally, the building occupants won't even know the source of the heat. They'll just be comfortable. We have several different ways rooftops and split systems can be applied. It's sort of a spectrum, where we have single zone systems on the left and move toward multiple zone systems on the right. First, the single zone two-speed system. The supply fan operates at a high or low speed setting. A thermostat in the zone is used to determine how much cooling or heating is needed. The rooftop unit is cycled on and off to provide cooling or heating, while the fan is adjusted between high and low speeds to maintain the zone temperature set point. Finally, the outdoor air damper position is set to introduce the required CFM of outdoor air for ventilation, adjusting its position as the fan speed changes between high and low. Or this damper might be opened further when it's cool outside for airside economizing. Here's an example of how a single zone two-speed system might operate. The top chart shows heating and cooling capacity, while the bottom chart shows supply fan operation. When the zone temperature is in the dead band, the supply fan operates at minimum fan speed. When heat is needed, the supply fan continues to operate at minimum fan speed, and the unit engages its first stage of heating. In the case of a heat pump, this is the first stage of heat pump heating. As the need for heating increases, the system responds by increasing the fan speed to its maximum setting, while also increasing the heat output by engaging the second stage of heating. A single-zone VAV system improves upon the two-speed single-zone system by implementing variable speed fan control. This allows the system to vary the amount of airflow delivered to the zone in cooling and possibly heating, therefore using less energy. A zone sensor is used to determine how much cooling or heating is needed. The rooftop unit controller adjusts fan speed and compressor operation to maintain zone temperature at set point. The controller also adjusts the outdoor air damper position to bring in the required CFM of outdoor air as the fan speed changes. Now, some heat pump units may require a constant volume of supply airflow through the heat exchanger during heating, while others might be capable of modulating airflow while heating. This could be accomplished with staged heat pump operation. Here's an example with 2 stages of heat. When the zone temperature drops to its heating set point, the first stage of heat is activated, and the supply fan modulates to maintain zone temperature at its heating set point. When the second stage of heat is activated, the supply fan operates at full speed. Both a single-zone 2-speed fan system and single-zone VAV system might be applied in the same way. Let's use a 2,300 square foot branch bank building as an example. Inside, there's a large lobby with tellers, several private offices, a conference room, break room, restrooms, and an ATM server room. This server room is going to be served by a separate ductless mini split system, and the restrooms will have their own exhaust system. One package DX heat pump rooftop will serve the entire building, as shown here as a single zone in yellow. Supply airflow is ducted to diffusers in the various spaces. Return air grills open to the ceiling plenum allow air to return. For this single zone configuration, a thermostat is installed in one location, the lobby. The single zone 2-speed system is commonly used for large open spaces, such as cafeterias, auditoriums, gymnasiums, warehouses, retail stores, or restaurants. It's simple and well understood. It can be used to condition a single space or set of spaces. Or multiple units can be grouped together to serve a large zone, like a warehouse. Comfort issues can occur if a single unit is used to serve a zone that is made up of several dissimilar spaces. The single-zone VAV system shares the same layout as the previous single-zone system. One rooftop to serve the entire building, and a single temperature sensor installed in the lobby. Single-zone VAV is a better alternative to a constant volume system. The addition of a variable speed fan allows the unit to reduce supply fan speed during periods of reduced load, which reduces fan energy use. But, like the 2-speed single-zone system from before, comfort challenges can occur because this system treats the entire building as a single thermal zone with a single zone sensor. To overcome this challenge, the design team might choose to install multiple smaller rooftop units, each with its own zone sensor. Here, we're showing 4 thermal zones with 4 different rooftops, each equipped with a zone sensor. This would provide more zones of control, but increases the installed cost, as well as the number of building penetrations and utility connections. Another option is to install multiple zone sensors and let the unit controller average the temperatures. The rooftop unit controller averages the readings to determine the required control action.
So, a single zone system would treat the entire branch bank as a single thermal zone. Next, Eric will review multiple zone systems, meaning the building has multiple thermal zones served by a single rooftop unit.
This system uses VAV terminal units and a rooftop unit or split system. Each thermal zone is equipped with a communicating zone temperature sensor and VAV terminal unit. The temperature sensor in each zone is used to determine how much cooling or heating is needed, and then the VEV terminal modulates the flow of cool or warm air to maintain zone temperature at set point. To provide conditioned air to the VEV boxes, we have a packaged DX rooftop unit. The unit draws recirculated air from the return air plenum and mixes it with outdoor air. This mixture is then conditioned and circulated through the supply ductwork and VEV boxes into the occupied zones. For this changeover hybrid system, a control system uses a voting strategy to determine whether the rooftop unit should supply cool air down the duct or change over to supply warm air down the duct. The controller on each VEV terminal votes based on the cooling or heating need of its zone. This means that the rooftop unit is providing only cool air for cooling or warm air for heating. This is the successor to the older changeover bypass system. So in the cooling mode, the variable speed fan modulates to maintain duct static pressure at a programmed set point, while the cooling capacity is modulated or staged to maintain the discharge air temperature set point. In the heating mode, the supply fan will operate at full airflow when the refrigeration cycle is reversed to provide heat. To allow variable airflow to the zones, but full airflow in the rooftop, an air bypass between the supply and return air paths is needed. This bypass will allow excess supply airflow to recirculate back to the rooftop unit. As the zone level VEV dampers modulate farther closed, the position of this bypass damper is modulated in heating mode to maintain the duct static pressure at set point. Due to this bypassed air, the discharge air temperature can become very warm, requiring the controller to limit heating capacity to prevent overheating. So let's return to our branch bank building example. One package rooftop serves the entire building, and the supply airflow is ducted to 4 VEV terminals, which each modulate airflow to each of the 4 zones. Zone number 1 is the north side of the building, which includes 2 private offices and a break room. The zone sensor is in one of the offices. Zone 2 includes the area behind the teller counter on the west side of the building. Zone 3 is the customer lobby in the center of the building. And Zone 4 is the south side of the building, which includes a private office, entrance vestibule, and conference room. For this zone, the sensor is in the conference room. Changeover hybrid requires a bypass damper, shown here ducted between the supply and return ducts. And a system control panel is used to coordinate operation of the rooftop unit and VEV terminals. This system controller is responsible for conducting the zone voting to determine whether the rooftop should supply cool air or change over to provide warm air. The changeover hybrid system allows one rooftop to serve multiple thermal zones with independent temperature control. It's probably more economical than installing multiple smaller rooftop units. But despite having multiple zones, there can still be comfort issues if the zones have dissimilar thermal loads. A drawback to the changeover hybrid configuration is that the rooftop unit must provide the zone heat unless the VEV boxes are equipped with terminal heat. The final configuration is a multiple zone VEV system with terminal heat. Here, most or all VEV boxes include electric or hot water heat. So rather than changing over to supply warm air, the rooftop unit continuously supplies cool air year-round. Zone heat is provided by the VEV units, but the rooftop unit is still equipped with heat. It can use the heat pump heat during morning warm-up mode. This is performed to warm a building prior to occupancy, perhaps after a cold night or weekend. Also, during normal operation in cold climates, the recirculated outdoor air mixture might need some heat to ensure cold air is not delivered down the duct to the VEV boxes. So the rooftop will use SCR electric or modulating gas heat to provide supply air tempering, which heats the supply air to a set point, perhaps 60 degrees Fahrenheit. The rooftop does not need an air bypass because the system relies primarily on the VEV boxes to modulate airflow and provide heat. This table shows the spectrum of single and multiple zone systems. The single zone systems do not need VEV terminal units or a bypass damper. Heat pumps can be applied across the board. VEV terminal units are required in the multiple zone configurations. A changeover hybrid system does require a bypass damper, but multiple zone VEV systems with electric or hot water terminal heat generally do not require a bypass. In our example building, one package rooftop supplies air to 4 VEV terminals, each with an electric heater. So zone heat is provided by the VEV boxes. If needed, the rooftop unit will temper the return outdoor air mixture. And the unit provides morning warm-up to heat the zones before people arrive. A system control panel, shown here mounted in the break room, is needed to coordinate system operation. The multiple zone VEV system provides good zone temperature control because there are multiple thermal zones, each with an independent zone sensor. And it can simultaneously provide cooling and heating, for example, heating the perimeter and cooling the interior zones. During periods of part load, the compressors can unload and fan speed can be reduced, saving energy, but it does require terminal units with heat. Next, let's discuss efficiency requirements. Historically, heating system output has been generally constant, regardless of ambient operating temperature. And efficiency has been relatively constant too. Here's an example. On the horizontal axis, you can see outdoor ambient temperature. On the primary vertical axis, you'll see heating efficiency expressed as a percentage, and coefficient of performance on the secondary vertical axis. Today, gas-fired heat exchangers are required to be 81% efficient, which means for every 100 BTUs of gas consumed, we get 81 BTUs of heat. Electric resistance heating is 100% efficient. All energy in becomes heat. This is a COP of 1. But heat pump heat output is a function of ambient conditions. How much heat can be removed from the ambient air? It is not constant. And we can see that as ambient temperatures decrease, the efficiency decreases. Now, to account for this, ASHRAE's energy standard, 90.1, sometimes uses 2 ambient temperatures in the minimum efficiency rating. Here's an excerpt from Standard 90.1 2022 for air-cooled packaged unitary equipment. Let's consider an example 12.5-ton heat pump rooftop with an auxiliary electric heater. First, cooling efficiency. The unit is 150,000 BTUs per hour, so it fits into this capacity range. And since it has an auxiliary electric heater, the minimum efficiency is 10.6 EER at full load and 13.5 IEER at part load. Heat pump units also have separate heating mode efficiency requirements. To express this, 90.1 uses coefficient of performance heat pump heating, or COPH. This metric is defined as the ratio of heat delivered divided by the rate of energy input in the same units. It's important to note that this does include auxiliary heat if that's being used at specific test conditions. For heating, we have 2 ambient temperature-based requirements. For our example heat pump, the COPH must be at least 3.30 at an ambient temperature of 47 degrees Fahrenheit and 2.05 COPH at 17 degrees. Ray is going to discuss some of these common terms next.
Thanks, Eric. In this segment, we'll review some common heat pump and dual fuel terminology. The balance point occurs when the heat pump can provide exactly as much heat as the building heat loss is resisting. At this point, the equipment will maintain the space temperature by running continuously. Above this point, the heat pump will cycle normally. The attached image represents the difference in the building load as a function of outdoor air temperature versus a typical unit's capacity. The vertical indicator, along with the intersecting variables, represents the balance point. Many heat pump controllers use logic to monitor the space temperature and manage the recovery rate. This logic may be performed in a conventional thermostat or by the equipment's microprocessor. As ambient conditions change, the controller will monitor the space temperature and recovery time. If the mechanical heating cannot maintain the space temperature, the logic will automatically enable supplemental heating. Trane light commercial unit products use a sequence called rapid recovery. The microprocessor will monitor the time it takes for the space to become satisfied. If the space temperature is not recovering towards a set point rate of 6 degrees Fahrenheit per hour or 0.1 degrees Fahrenheit per minute, supplemental heat is enabled. A 9-minute stage-up delay is provided for each stage to allow time for recovery to begin. Stages of heat are enabled as necessary to meet the heating demand. The switchover sequence takes place when the outdoor temperature is equal to or less than the heat pump heating lockout set point. In this mode, the compressor heating outputs will be disabled and the auxiliary heating is used to temper the space. The auxiliary heat may be any form of heat other than the primary heat type. In this case, we reference both electric resistance and gas heat options. The supplemental heat term is closely related when referencing auxiliary heat. In this case, both terms are referencing the same heat source. The primary difference is how we reference them in the sequence. For example, in an air-to-air system, the help that a heat pump gets is called supplemental heat. The heat pump itself is the primary heat, and the auxiliary heat source may be electric, propane, or natural gas. Electric heat is a popular choice because it's easily adapted and requires no additional utilities. In some cases where natural gas is available, traditional cooling gas-electric units may be replaced with an eco-friendly dual-fuel option. This allows a heat pump to be placed into operation while taking advantage of an existing gas service. This is a perfect option when considering existing electrical services or load sizing requirements. Next, we'll take a look at net heating versus gross heating capacity. When considering a heat pump applications, it may be common to see a higher net heating capacity than a gross heating capacity. The inverted capacities may seem counterintuitive, but not with a heat pump. In the cooling mode, the indoor motor heat impacts the cooling capacity. The additional heat is captured in the equipment's net total capacity output. A heat pump, on the other hand, welcomes the additional heat source. The result of the additional heat impacts the leaving air temperature and may result in an inverted gross versus net capacity value. The air-to-air heat pump coefficient of performance, or COP, can be summarized in one word: efficiency. For example, a resistive heater provides 1 watt of electric heat for every watt purchased. This is called 100% efficient, or a COP of 1. The output is the same as the input. With a heat pump, the efficiency may be improved as much as 3.9 to 1 for airside applications with typical equipment. This means that when 1 watt of electrical energy is used in the compression cycle to absorb heat from the outside air and pump this heat into the structure, the unit can furnish up to 3.9 watts of usable heat. This is a COP of 3.9 to 1. This equates to a nearly 390% improvement over electric heat. These COP values will vary by manufacturer. For that reason, we recommend reviewing each manufacturer's product-specific catalog. Let's review this in more detail. The attached image represents the difference in the building load as a function of outdoor air temperature across the horizontal axis versus a typical unit's capacity as shown on the vertical axis. The blue line represents the COP as a function of outdoor air temperature, while the black line represents capacity. As ambient conditions change, so does the capacity. Keep in mind that heat pump efficiencies are tested per ASHRAE 210-240 for equipment up to 65 MBH, and 340-360 for units up to 300 MBH. The standard COP test conditions are 47 degrees Fahrenheit for high and 17 degrees Fahrenheit for low. Another common component is the four-way or reversing valve. This is a mechanical switching device that redirects the discharge gas in the proper direction to either heat or cool the space. In the cooling mode, the gas is directed to the outdoor condensing coil before making its way to the evaporator. In the heating mode, the gas is directed to the indoor coil before making its way to the outdoor coil. With heat pumps, outdoor coil frosting is a perfectly normal occurrence. The outdoor coil typically operates between 15 to 20 degrees cooler than ambient temperatures. This operating range is dependent on the refrigerant type and density. For that reason, the rate of frost accumulation depends on the ambient conditions. Shown in the attached image on the left is an example of a coil frosting. Conditions that would accumulate additional frost would be a 50-degree dry bulb with a 48-degree wet bulb. At these ambient conditions, the logic allows defrosting when the outdoor coil reaches its permittable threshold of 32 degrees. As frost begins forming on the face of the coil, the heat transfer process becomes less effective. This is when the coil defrost mode switches the flow of refrigerant, utilizing the heat of compression from the cooling cycle, thus thawing out the outdoor coil and removing any remaining frost as shown in the right-hand image. An example of a coil frosting condition that would accumulate less frost would be a 30-degree dry bulb with a 21-degree wet bulb. At these conditions, the ambient air is considerably drier, resulting in less frost accumulation. The heat pump ultimately retains its effectiveness due to a less restricted coil. In the next slide, we'll discuss the two common defrost methods and review how the defrost sequence takes place. There are two common methods used for outdoor coil defrosting: demand and timed defrost. First, we will review the demand method. Demand defrost monitors the ambient conditions, along with the mechanical system temperatures, before initiating a defrost sequence. It activates the defrost cycle only when needed based on the condition of the coil, saving energy by minimizing unnecessary defrost cycles. This illustration indicates that two conditions must be met before any defrost cycle can take place. The ambient temperature must be below 52 degrees Fahrenheit, and the outdoor coil must be below 33 degrees Fahrenheit. Once these conditions are met and the timed sequence has expired, the defrost sequence may be permitted. The unit will cycle the four-way valve and stop the outdoor fan. This process allows the heat of compression to melt any accumulated ice. Once the defrost conditions are met and the defrost termination temperature is satisfied, the heating sequence will resume. The second method of defrosting is a timed versus temperature method. The timed versus temperature sequence is uniquely different from the demand sequence, as it does not use a comparative decision to enter the defrost mode. This sequence is allowed anytime the coil temperature is below the enable threshold. The defrost module monitors the compressor's accumulated runtime and will initiate a timed defrost sequence for every 30 minutes of accumulated compressor operation. In some cases, the defrost duration can be adjusted to meet the regional conditions. Now let's take a moment to review the differences between heat pumps and the traditional cooling system coils. You might ask yourself, what's the difference? When we describe a heat pump, we must be sure to use the proper coil terminology. A typical cooling unit uses an evaporator and condensing coil. During the cooling mode, heat energy is absorbed through the indoor evaporator and is then rejected through the outdoor condensing coil. A heat pump uses the same refrigeration cycle but changes the refrigerant's flow and each coil's role. The heat pump cycle absorbs heat from the outdoor coil and transfers this heat to the space. Let's review this process in a little more detail. How does a direct expansion AC unit that cools in the summer transfer heat in the winter? With a few exceptions, the two processes are nearly identical. A compressor pumps refrigerant through a reversing valve that is typically directed to the evaporator coil. In the heating mode, refrigerant is redirected to the indoor coil. The refrigerant is then pumped the opposite way through the indoor coil and bypasses the indoor metering device. The indoor fan moves return air across the indoor coil. In this process, heat energy is rejected from the high-pressure, high-temperature gas. As the high-temperature gas moves through the indoor coil, the refrigerant begins to subcool. In this process, heat is rejected and the state of the refrigerant begins to change. The result of this change is a high-pressure warm liquid. The high-pressure warm liquid now makes its way to the outdoor metering device. In this step, we see the direct expansion process take place. The subcooled refrigerant is forced through the outdoor TXV, where the direct expansion process instantly changes the state of the refrigerant. The refrigerant begins to boil and change state once again. This process forms a low-pressure, low-temperature gas. As the gas makes its way through the outdoor coil, the outdoor TXV controller throttles the metering device to maintain a designed superheat. This device meters the proper amount of refrigerant and maintains the true suction pressure. As the outdoor coil in this process is typically operating at temperatures 15 to 20 degrees below the outdoor temperature. During this process, the outdoor fans pull air through the outdoor coil and the heat energy in the ambient air is absorbed by the refrigerant. This is when the thermal transfer of heat moves from warmer to cooler. At this stage, the refrigeration cycle is complete and may begin again. And with that, I turn this back over to Abby for an overview on how to select a heat pump.
Thanks, Ray. Really good information. Determining the right size for a heat pump isn't completely straightforward because the refrigeration system is sized for both cooling design and heating design with the possibility of needing auxiliary heat. However, there is a general method to guide you in selecting the appropriate size. The first step is to perform a load analysis. Based on the output, determine the necessary cooling and heating load at design day conditions. Next, select the rooftop unit at the design cooling load condition. Using information from the manufacturer, you can now determine the net heating capacity of the selected unit at varying ambient temperatures. Last, decide if the heating capacity provided by the unit will be enough to cover the required heating load. If not, auxiliary heat will need to be added. In the next few slides, I'll show an example of how to demonstrate the process of sizing a heat pump unit. And we'll wrap up with some additional tips to assist you in accurately determining the right size for your heat pump. For this example, we've determined the heating load to be 53 MBH. And for reference, the cooling load is 58 MBH based off the standard 80-67 entering conditions and the 95-degree Fahrenheit ambient, and the same CFM we are calling out for heating using the manufacturer's catalog or Trane Select Assist. Based on our cooling load of 58 MBH, we will need to determine the required cooling tonnage of our unit. Do this using a standard conversion formula of MBH over 12, which is tons of cooling. So for our example, that's 58 over 12 equals 4.8 tons. And to make this number neat, we round up to 5 tons. Using this as our baseline, we can use either the manufacturer's catalog data or a performance program such as Trane Select Assist to determine the unit's heating mode output. With an outdoor winter design condition of 22 degrees Fahrenheit and return air temperature from the space of 70 degrees Fahrenheit, the manufacturer's data shows that the unit in heating mode will provide about 39 MBH. And because 39 is less than the building's required heating capacity at winter design conditions of 53 MBH, an auxiliary heater must be selected to supply the remaining 14 MBH of heat required. For auxiliary heat sizing, you must pay attention to both the additional heat needed as well as the voltage of the heat pump of the unit. Varying voltage correction factors must be applied based on the job site electrical service. Taking into consideration the data from the previous slide, our example unit is a 460-volt unit, which requires an additional 14 MBH of heat based on our delta T calculation. Referring to the manufacturer's data, determine what auxiliary heat options are available and which best applies to our example system. This example 5-ton unit has a 6 kW minimum option, which provides 20.5 MBH of heat at 480 volts. It's important to remember to derate the auxiliary heater output based on the job site voltage. Since our example job site voltage is only 460 volts, the 6 kW electric heater will need to derate to 5.5 kW or 19 MBH based on the data from the correction factor table shown. The available 19 MBH of heat will still satisfy the required 14 MBH of required auxiliary heat. Now, why didn't I upsize the unit seeing as it needed supplemental heat? Here's where it can get tricky. The goal is to match the heat pump's capacity during extreme temperatures with your building's largest heating or cooling load. But there's risk in both undersizing and oversizing. Undersize the unit and it won't be able to keep up with peak cooling demand and subsequently strain the system. Oversize the unit and you have constant on-off cycles and could experience issues with humidity control. So with this, there are several key takeaways. As with most things in life, kind of like a checkbook, there's a balance. Don't automatically replace an older HVAC unit with the same size. Energy efficiencies are changing at an ever-growing rate, and it could mean you could get by with a smaller system. Don't assume which way you will go if adjusting the tonnage because every situation is different. So use the data to guide you. Another way to help is to note the switchover temperature that Ray discussed earlier in the presentation. If design day heating temperature is above the switchover temperature and there's enough heat capacity, then no auxiliary heater is required. If design day heating temperature is below the switchover temperature, then take the required heating capacity from your load calculation and subtract the heat pump heating capacity in the manufacturer's table or software and size the auxiliary heater to handle the difference. And the same process would apply for sizing a dual fuel unit. As for dual fuel, though, check with your manufacturer's sequence of operation to know if the gas heat will run simultaneous to the heat pump heating operation. For these units, the heater should be designed based upon total heat loss. And since we just reviewed the general guidelines to sizing, let's turn it over to Greg, who will discuss energy modeling for these systems.
Thank you, Abby. Now let's look at a real-world example of a classroom across many geographies and ASHRAE climate zones to compare various rooftop system configurations. In our example, we have a single 30-person multi-purpose classroom being served by a single high-efficiency rooftop unit with 470 CFM of outside air based on ASHRAE 62.1 and a desired space temperature of 73 degrees Fahrenheit for cooling and 70 degrees for heating. We are comparing 4 rooftop system configurations. First, a gas-electric rooftop unit where heating is provided by natural gas and cooling by electricity. Second, an electric rooftop unit where heating is provided by electric resistance heat and cooling by electricity. Third, a heat pump with electric auxiliary heat. And lastly, a heat pump with auxiliary natural gas heat, which is often referred to as a dual fuel heat pump that uses natural gas as the auxiliary heat source. We'll be comparing these systems from a load, energy, and CO2e perspective. Let's dive in and see how the various rooftop configurations perform in different geographies and ASHRAE climate zones. The chart on this slide shows the various locations modeled with their corresponding ASHRAE climate zone, cooling dry bulb and wet bulb, and heating dry bulb design temperatures, the rooftop unit cooling capacity, as well as the electric and natural gas utility rates and resulting cooling and heating loads. We wanted to get a good cross-sampling of ASHRAE zones, so we picked 7 cities across North America. The cities include Orlando, Florida, Atlanta, Georgia, Los Angeles, California, St. Louis, Missouri, Nashville, Tennessee, Seattle, Washington, and Toronto, Ontario. In addition to spanning ASHRAE climate zones, these locations have different utility rates and CO2 emissions factors that play a role in the energy and CO2e analysis. But in the interest of time, we will focus primarily on 4 cities that will give us the widest sample representation of climates. These are Orlando, Florida, Los Angeles, California, St. Louis, Missouri, and Toronto, Ontario to get a good representative sample. The first step, using the ASHRAE 0.4% weather data, we calculated the cooling and heating load using an 8760-hour load modeling tool. For our example, we used Trane Trace 3D Plus to calculate. The size of the rooftop unit and cooling capacity varied from 3 tons in Los Angeles, California, to 4 tons in St. Louis and Toronto, Ontario, while a 5-ton unit is required in Orlando, Florida, to meet space design conditions. From the load calculations, we were able to determine if the location is cooling or heating dominant or both, where the heat gain and heat loss are relatively equal. The unit in our example is sized to handle the cooling load. Next, we determined a blended utility rate for electricity and natural gas. The electric utility rates vary from 24 cents per kWh in Los Angeles, California, to 11 cents. Similarly, natural gas cost per therm varied from $1.47 per therm in St. Louis, Missouri, to $1 per therm in Toronto, Ontario. Let's go through the 4 cities, starting with Orlando, Florida, looking at operating energy and CO2e performance. Orlando is a cooling dominant location with a small amount of heat required. As we look at the various locations in depth, we will use the gas-electric rooftop unit as our baseline or system to compare to. There is not much difference in annual operating energy across the 4 configurations. However, when we look at CO2e, a heat pump with either electric or natural gas shows a reduction of 24% CO2e, when compared to a traditional gas-electric rooftop unit. Next, let's travel west to Los Angeles, California. Los Angeles is also a cooling dominant location. Now we start to see a larger difference in the utility spend across the 4 system configurations due to higher electric utility rates, but the CO2e for both the heat pump with auxiliary electric and natural gas shows a 42% and a 46% reduction respectively. It is important to note that local codes and California Title 24 must be considered when selecting system configurations in California. Now we move to a mixed cooling and heating dominant climate in St. Louis, Missouri, where the cooling and heating design loads are similar in magnitude. Due to the utility rates used, a heat pump with natural gas auxiliary heat saves approximately 9% in annual operating costs, but due to the SRMW grid emissions factors, where the CO2e is 58% greater than the baseline gas-electric rooftop unit on an annual basis. Utility rates and the cleanliness of the utility grid can play a factor in unit selection. If the owner's goal is to decarbonize, then a traditional gas-electric unit results in the lowest CO2e. However, if the goal is to save annual operating costs, a heat pump with auxiliary natural gas heat has the lowest annual operating costs. Lastly, let's visit our friends up north in Toronto, Ontario. Obviously, the winter design in Toronto is the coldest of the cities analyzed and offers the most hours of heating operation. The baseline gas-electric rooftop unit offers the lowest annual operating cost of the 4 systems analyzed, whereas a heat pump with auxiliary electric heat costs 135% more annually to operate, but has an 89% annual reduction in CO2e, which is substantial. Let's take a closer look at the input and output for the 4-ton rooftop serving a classroom in Toronto, Ontario. We use Trane's heat pump calculator to get the energy and CO2e data using the heating and cooling loads generated by Trace 3D+. The graph on the left gives us an idea of load versus outdoor air temperature. The balance point between heating and cooling is approximately 55 degrees Fahrenheit. Below 55, there is a heat call, and above 55 degrees, there is a cooling load, thus a call for cooling. The graph also shows both the heating and cooling design day temperature, which in our example for Toronto, Ontario is 0 degrees Fahrenheit for heating and 89 Fahrenheit for cooling. The right-hand box shows the rooftop unit configuration input used in the calculations. For further information regarding the heat pump calculator, reach out to your local Trane office. On the left, we show another useful output for the designer, which is the bin hour temperature data, showing how many hours are at various outdoor temperatures throughout a calendar year. The graph on the right shows how many cumulative hours both heating and cooling are called for during a calendar year from January through December. As we look at the 4 cities, it is apparent that one size or system type does not fit all, and the proper unit selection is based on several factors. One being the owner's goals or area of focus. Is the owner looking to save as much operating energy as possible? Here we see an annual operating cost comparison for the 4 cities we analyzed for the 4 rooftop system configurations that we compared. Or does the desire to electrify and/or decarbonize overrule the need for the lower operating costs? Utility costs and the cleanliness of the grid also play a determining factor in selecting the right system for the project. Here is a look at the 4 cities from a CO2e standpoint, showing the 4 system configurations in comparison. Another factor that may play a role in system selection is whether the project is new construction or a remodel or retrofit. New construction offers the opportunity to design from the ground up, particularly relative to the electrical panel size. In a remodel or retrofit situation, you may or may not have enough electrical services to support either an electric or heat pump with auxiliary electric heat, particularly if you are upgrading gas electric rooftop units, where a heat pump with auxiliary natural gas heat may. The good news is, engineers and designers have many system configurations and options to choose from today to satisfy the project and owner's needs. I will now pass it over to Jeannie to bring us home.
So that's our program on modern unitary heat pump applications. We hope you found it a helpful way to learn about heat pumps. Please fill out a survey to let us know what you thought of today's program. And as always, the bibliography included with this program provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest self-paced online courses at the Trane Education Center. Finally, for those of you viewing in person, please ask your local host about details for the 2025 Engineers Newsletter schedule. Thanks for joining us today. We look forward to seeing you next time.